So my purpose here today is to go over the basics of the MO theory, at least writing these very simple bimolecular diagrams from two atoms coming together like nitrogen or oxygen, and try to show you how that opens a door for something called gap theory or band theory that tells us something about the conductivity of chemicals, and of course their ability to absorb wavelengths of light. That's right. Also, we're talking about gaps that exist between orbitals that are created when these orbitals are very similar or interconnected throughout the molecule. So I'm trying to take you from very simple MO theory, okay, through something called band theory or gap theory. And through that, we'll look at conductivity and the ability to make these gaps small enough to basically absorb wavelengths of light, and then take you eventually to the idea of how transistors work. Okay, now transistors I'm not going to get to in this lecture, but I'm going to take you from the MO theory to the band or gap theory, and then eventually to transistors. Okay, so I need to get through these two. So let's start. Now I did molecular nitrogen gas in class, and we know through the valence shell theory that nitrogen is triple bonded, putting dots to a page or paper, and then of course counting our valence electrons and sharing electrons, we need to get to an octet. Okay, and when we do this from molecular nitrogen, we get the same thing. I want to get to oxygen, particularly. Now we did it in class, but for some of us it was too fast. Okay, so what we're looking at here, party people, is we're looking at an MO diagram, and what we're going to do is we're going to put electrons from the two atoms coming together. So again, think of an atom of oxygen, another atom of oxygen. They're going to collide, physically collide, and orbitals are going to interact. And when they interact, we're going to have bonding orbitals, which are more stable, and anti-bonding orbitals. Remember, this is not a valence bond theory. This is dealing electrons as waves and doing mathematical equations for the energy of these orbitals when they constructively interfere, okay, which is a more stable scenario with electrons between two nuclei, and the scenario where they destructively interfere these waves, okay, and create electron densities outside the region between the nuclei. All right, so how do we start this? Well, consider, and it's very important you understand, that this part of the diagram is the atoms coming together. So if I scroll up, all right, I get the atoms on this side. So there's an oxygen on this side, and its configuration is 1s2, 2s2, 2p4. And the oxygen over here, okay, there's another oxygen that's coming together, and that's the other oxygen here, okay, and it's 1s2, 2s2, 2p4 as well. So real quickly, let's put the valence electrons in. All right, we can guess what's going to happen with the 1s2 as we did hydrogen today, but we have 2s2 here. So 2s2, I'm just putting the electrons in. And then on 2p4, okay, so I'm going to put these in. 1, 2, 3, Hud's rule, 4. I guess I should go blue here. 1, 2, 3, and 4. And I guess I should keep things the same. We'll do blue for the left oxygen. And I'm filling these orbitals, these 2s orbitals, because I have what? In the atomic orbitals, I have a filled orbital of s. In the atomic orbital, I have 4 electrons in the p. Same. Okay, so now we're going to do is we're going to fill and talk about the two possibilities when these waves interact. Of course, the lower energy, more stable scenario is the sigma, and it's always going to be lower. And of course, I'm going to take one of these electrons, so we'll go up, and take one of the reds and go up or down to show opposite spins. And so I've took half of these, and the other half go here. All right, so the two electrons in this left oxygen, one went to the bonding, one went to the anti-bonding, and the opposite happened to the red oxygen. Remember, they're going to come together, and their orbitals are going to interact, and there's going to be constructive and destructive. Okay, so we're almost done. Now we're going to take, again, these four. So I got one. Let's go down here. And I'll take three of these, showing opposite spins. And you notice I used three. I need one more. And same thing here, one more, Hudd's rule. So if you notice, I had a total of 8 electrons in this 2p, total 8 electrons from both atoms coming together. And I took 2, 4, 6 here, and then I have my 8. So notice 4 of the blue fill this way, 4 of the red. And you notice we filled our bonding orbitals for a p. One is the sigma, and the other is the pi. And you know the first bond is always the sigma, the second and third is the pi. Now, if you notice something, party people, when we do bonding order, okay, bonding order is equal to the, essentially, the bonding electrons divided by 2 because a bond is a pair, minus the anti-bonding electrons, I'll do a little star here, over 2 because a bond is a pair. And notice how many bonding electrons do I have? I have 2, 4, 6, 8. Who do we appreciate? MO theory, of course. 8 over 2 minus the anti-bonding. Well, we have 2s star there. That's 2 there. And then we have this scenario, the more unstable. So we have 4 altogether for anti-bonding electrons over 2. And you get 4 minus 2, and you get a bond order of 2. And that speaks to the fact that oxygen has 2 bonds between its one region of 2. All right, we know that from valence bond theory. So what's the big deal? Well, the big deal is, okay, we know from experimentation that oxygen liquid is actually a little blue, lightly colored blue. And how can that be? Well, we can see from the MO theory that some of these electrons, if they're giving a color of light, that means they're absorbing some wavelengths of light, right? So some light of all frequencies, of all photons of different frequencies are hitting, and then not all of it's coming out. You're seeing the blue come out because, well, maybe we're basically absorbing the yellow part of the spectrum, which means yellow photons, if I can do this, okay, are hitting this compound and giving these electrons energy to jump up. Okay, so they're absorbing that. All right, and so there's a gap being made between the bonding 2p orbitals, the pi 2p orbitals, and the pi anti-bonding pi. So this gap really isn't big. It looks big in my drawing, but it's big enough that it can absorb a wavelength of light, or I should say small enough, because if it's too big, okay, wavelengths of light, which are tiny, okay, would be enough to move this. So the gap is small enough so that the wavelengths of visible light can be absorbed exactly. Remember, to get from one position to another is an exact amount because it's a quantized effect. The atom is quantized. So the color given off is the idea that we have this little gap. Remember, I talked about the fact that MO theory leads us to something called gap theory or band theory. And again, what's happening is we're creating a little gap here for oxygen that we would never, ever consider if we didn't use this theory. And you say, well, why, Mr. Grodsky? Well, if you take oxygen and it's 6 valence electrons, and we put it with another red oxygen, and we use valence bond theory, what we're going to get is what we expect, the double bond. Remember, every what? Oxygen, by having a double bond, feels like it has its 8 there. It's the valence shell that we talk about. So this is expected. If you think about oxygen as we did here, this blue one is what? 1s2, 2s2, 2p4. What does that 2p4 mean? Well, that 2p4 means that we have 4 electrons in our 2p orbital. I know I drew this before, but I need to make this point. And then we have a red one, 1s2, 2s2, and also 2p4. And we still have 4. And so what happens, party people, is we're going to have what? A sigma bond with one of the p's, and by them doing what? Overlapping, they feel like they have two, and so this probably is this, one of these is a sigma bond, can't know for sure, and the other one is the pi bond. So you can see that unhybridized p orbitals basically either overlap directly or indirectly overlap with the pi bond to make them both feel like they have filled p orbitals. And that's the valence bond theory. So when these guys overlap, this guy feels like there's another one, and this one feels like this. So they all feel like they have another one, which means where is the what? Where is the lone pairs? If every single oxygen in this setup here feels like they have the octet, which means what? They're 2s2, 2p6 by sharing. Okay, remember that p orbital overlapping another p orbital to feel like they both have what? 2. And the same thing with the what? The other p orbital giving us the pi bond, right? This is the sigma and this is the pi. Why I'm drawing it off to the side, not really sure. I guess I'm being artsy. So they both feel like they're filled. So where do we get alone singlets or occupied, unfilled orbitals here? We don't in this theory. So valence shell theory does not predict that oxygen would absorb wavelengths of light because all of its orbitals are filled in the valence bond theory when they bond to get this octet. Whereas in molecular MO theory, more advanced theory, this shows us that there are, okay, unpaired electrons in these antibonding orbitals that give the ability to absorb wavelengths of light. More importantly, though, as I will show you in class, okay, this determines the idea that oxygen molecules are what? Paramagnetic. Remember, we talked about this. Having lone pairs means you do not have another electron in this orbital of opposite spin to cancel out this spin. So these spins will go together, creating a paramagnetic ability, meaning that they are affected by a magnetic field, okay? Which I will show you with the liquid oxygen demo that I have taped or have a video for. Pretty cool. And again, that's only shown with MO, not with valence bond theory. So the MO theory gives us more information or fills in the gaps, so to speak, no pun intended. All right. So in this case, in this diagram here, okay, the MO created this kind of ability to have a gap to create a blue color and gave us these lone pairs, okay, so that we can basically understand that and explain or at least demonstrate through this theory the paramagnetic magnetic ability of oxygen that otherwise would not be. So where do we go from this? Well, understanding this opens the door for something called gap theory, okay? Now, I know we said that this idea of having anti-bonding orbitals in this case allowed for us to understand a gap that was created, but there's more to it in gap theory, but it's it's based upon, I should say, on MO diagrams. So let's get to it. So here I have a tube hanging in the class, and I'm going to add some liquid oxygen. Look at the color, it's a slight blue, okay? So I'm going to add some of that. It's about 183 degrees Celsius, okay? And that's tough to see, but it is a light blue. It's not like, you know, royal blue. And what happens is, of course, you get frost on the outside, so it's hard to see it sometimes. But it is a slight blue hue. And I make it with liquid nitrogen. So in any case, what's really cool is because of that lone pair of electrons predicted by MO theory, but not predicted by valence bond theory, okay, a magnet can interact with those two lone pairs in those anti-bonding orbitals. So here I come, and you can see that there's paramagnetic ability. Okay, really cool. All right. and no pun intended, probably was a pun intended. So yeah, so essentially, again, due to the unpaired electrons in the anti-bonding orbitals, again, with valence bond theory, we don't have that. So that little gap from bonding to anti-bonding is enough to, number one, have its blue color, but also give it its paramagnetic spins, or its parallel magnetic spins, as I'm trying to read. All right, so I think you get the point. All right, so what we have here is a picture, maybe, of an MO diagram, okay? And so we're looking at if you look carefully, we have lithium, and then we have lithium 2. So this would be the atomic orbital diagram. It has one electron. Remember, lithium is 1s2, 2s1. We're just going to deal with the valence shell. Okay, now this one electron is in the s. Now in lithium bonds, as we saw, two electrons go in the what? The sigma 2s orbital. And it only has two. Now if you add more atoms, like L4, what you're going to do is you're going to add more orbitals. You see, you're going to add what? Well, 4 atoms, okay, are going to be 4s orbitals. So you're going to make well, actually going to make 2 sigma. So 4 atoms come together, okay, each with 1 electron, right, in the outer shell. If you put them together, you're going to make 2 new bonding orbitals, okay? So what you're going to see is we keep putting our single electrons, and what we do is, essentially, if we keep somehow interconnecting these atoms, okay, we start getting what we call a continuum. So as we add more and more lithiums, now lithium's a metal, and metals interconnect to make solids. And as they interconnect, okay, where one lithium starts, another starts, we're kind of making a super molecule. Now, they don't make molecules. We learned earlier on there's this face-center cubic and body-centered type of arrangements. But the bottom line is we're creating bonds between the lithium atom. They're metallic bonds. And you may have learned that there's a sea of mobile electrons when we have metallic bonding. So MO theory shows us that when I put these guys together, I'm just putting more and more what? Bonding orbitals together. And of course, lithium-18 is small. If I've got a gram of lithium that's stuck together by metallic bonding, there's a heck of a lot more than 18 of them. So these individual energy levels start blending together as you add more of them until, like I said before, you have this gap, okay, or bonding gap, okay, or this continuum. So this becomes electrons that are able to basically move through this entire region and act as a single energy level, okay? So it's a continuum. So electrons don't have just this energy. They're basically able to move throughout all the orbitals. They're essentially at a single quantum level of energy that's described from this region here to, let's say, this lower energy. So there's a continuum. You can't say where one starts. They kind of all are interlapping. So basically, if you remember in your earlier chem class maybe that metallic bonding, we have this sea of mobile electrons. If I have the nucleus and electrons are able to move throughout the entire crystal structure of a metal, we said that they're held so loosely, these electrons are free to move all the way around, okay? And when they move all the way around, that's the reason why they have conductivity. These electrons are loosely held and they're able to move throughout. Well, that doesn't really move throughout. They actually have this continuum of energy that they can move through here and higher. So they have a great swath of energy because they're able to kind of migrate through all of these orbitals that are blending into one, okay? Now, the anti-bonding region, okay, never gets any electrons in this scenario, okay, because we're always adding an electron to another bonding orbital. So we have room here. But what's really important is the anti-bonding region also becomes a continuum as well. And we call this the conductive band. This is sometimes called the valence band. These are where all the valence electrons, and we call it a band because they're not in one energy level. They're in basically a continuum of energy, able to exist through all of these orbitals one the same. So it's kind of like all of these orbitals, by putting together your MO diagrams, are blending into just one big region of electrons that all have the same energy level, okay? And if the anti-bonding do the same thing, and we have a continuum like this, it doesn't take much energy, okay, for an electron that's in this gap to get into this gap, this band, if you want to call it. A continuum is a band of orbitals, in this case, anti-bonding orbitals, that again, as we increase the number of atoms that are interconnected, this gets smaller and smaller and smaller until essentially you've got electrons that can exist in this continuum, all right, acting as a single, all these electrons acting as if they have the same energy. But to get to this higher energy continuum or band, yes, you would need energy. So things that conduct electricity very well have very small gaps between these continuums. And again, they're built because these MO diagrams are stacking on each other. Okay, very important. This happens all the time in metals, because in metals we say metallic bonding, okay, but really what it is we're creating a continuum for electrons to exist throughout the entire molecule. And yes, they're able to flow very freely throughout this band, but more importantly, okay, when they really, really move, conductively speaking, a little bit of energy is inputted, like a charge or electron volt, and they can pop up into this band here. And I'll explain that next. But what I want you to get from this slide is that if you can stack these atomic orbitals, these bonding orbitals and anti-bonding orbitals, as you add more atoms together, okay, you create a basically one energy level that all these electrons can exist at. Now, of course, it's a range of energy, but bottom line is all these electrons in this energy, in this area, okay, are at the same quantum level. All right, so let's continue on. So here's another example. Okay, now this is the 2s bonding orbital, and this could be the 2p bonding orbital. And you can see what we have here is we have overlapping continuums that occur, which means electrons can freely get from one to the other. Okay, so there's overlapping of these bands, and that's what you see with metals, is metals have overlapping of bands, meaning there's a way for these electrons to easily get to the higher energy position. And if they can easily get there and get excited very easily with a very small, in this case, no gap, they overlap, these are great conductors, because with a little bit of energy, they can get to the next higher energy level. Now, showing you the anti-bonding, but this is the different type of P's that would overlap as well. Okay, and look at the size of the 2s bands. Okay, so that's what's happening here. Let's continue on. All right, moving forward, what we have here is we have this valence band, we like to call it. All right, and this is the conductive band. Okay, this is the place where we have either an anti-bonding orbital, or it could be another bonding orbital that it can jump to. All right, the bottom line is, with a little bit of energy, electrons can what? Jump to the vacant band, be excited. When they jump back down, they can give energy off to readmit one. Now, let me just try to make some sense to that. So this really gives us a better view of how metals conduct electricity. So let me just make sure I get a nice little color here. So let's say I've got an electron here, and with some energy, I make it jump to the vacant band. That's excited, and then it won't take that much energy. Why? Because these gaps are really small. Sometimes they actually overlap. So this will jump down. When it jumps down, it releases what? Energy for another electron in the vacant, in the filled band or the valence band to jump up It's excited, it jumps back down, it releases energy for another electron to go up, and that's how charge is basically conducted. We're constantly exciting electrons with a little bit of tiny energy. Don't need much if what? The gaps are really small between the two bands or they overlap. Okay, so therefore it doesn't take much for the electrons to get to this higher energy position. They jump back, give off that little energy, and that can what? Re-excite the next electron who jumps up, is excited, jumps back down, gives off energy, and that's how essentially electricity or electrical potential moves down through in all directions, okay, a metal. We're pushing electrons into this vacant or higher energy level band, assuming the gaps are small enough. If the gaps become too high and we too much energy to get this electron, you can guess what we have now is an insulator, really important. So when we look at two metals, lead, in this case a nonmetal diamond, we know metals, okay, doesn't take much energy, let's say, to move an electron from the filled band or vacant band to the next band because the gap is small. Whereas the gap for a nonmetal is much higher. Very, very interesting. Carbon being a nonmetal, because it has a high ZEF, what does that do? Can't get away from it. It makes the gaps bigger. It pulls in these electrons in this band. And therefore the gap between the bands, the continuums, are so big that it has a difficult time for electrons to get here. And that's why carbon diamond is a terrible conductor of heat and electricity, whereas lead is much better. Okay? So the properties of our nonmetals, our small atoms with high ZEFs, are terrible conductors because that high attractive force electrons have contract these electrons closer to the nucleus and make these bands smaller, make these continuums so smaller that the gap from this continuum to the higher energy is too big. Sometimes they call this energy region the forbidden zone, okay? All right, and that's the area electrons can have, all right? And it's all predicated about, you know, the structure of the composition of the substance and, of course, the effective nuclear charge electrons feel. Okay, generally metals like lead have smaller gaps. Nonmetals have bigger gaps, and that speaks to how hard it is for these electrons to get excited and therefore jump back down and re-excite another one. And therefore, these are terrible conductors, where lead is better. Okay, moving forward. Now you can read these. I have this same exact presentation on the site here, but really important point here, so I want to really kind of read it to you. Band gaps are essentially leftover ranges. So when you have a gap, okay, in a, so you have the filled or valence band, and then you have a gap for the vacant band or the conductive band. So here's our band right here. So these gaps or forbidden areas are basically leftover ranges of energy not covered by any band. And it could be because we're dealing with very small orbitals, okay? And like the core electrons are held tighter to the nucleus, they attract them more. So therefore, they're going to be smaller, and that could be some of the reasons why. But the result of finite or definite widths of energy bands. So band gaps that we have are leftover ranges that are not covered by another continuum. Okay? So the widths of these gaps depend upon the degree of overlap of atomic orbitals. So very important. Two adjacent bands may not simply be wide enough to fully cover their range of energy. So this might be a 2p and this might be an s right here. All right. For example, the bands associated with core electrons are extremely narrow due to the small overlap between adjacent atoms. So we know that n equals 1. Those are tiny, tiny orbitals. So their overlap is going to be so small compared to what? Bigger orbitals. So therefore, they have, of course, a smaller band. And therefore, that creates bigger gaps earlier on. All right, so higher bands involve larger orbitals with more diffuse electrons, more overlap, actually they're weaker covalent bonds, and become progressively wider at higher energy. So there are no band gaps at higher energy, kind of blend together. So the bigger the gap close to you are, the more electrons, and these orbitals are small enough. Okay, so in any case, moving forward. So when you have a single atom, you have atomic orbitals, there's definitely a finite amount of energy to go from a 3s to a 3p. Now, these 5 atoms, if their orbitals can interact, and there's definite ways they can, if they're solids, which means they're a continuous connection of these things like lithium or metals, and even, you know, even like something like graphite, where carbon is bonded to carbon, nonmetals bonded to nonmetals in that arrangement, create these continuums. As soon, like, of course, if I only have 5, okay, we start stacking these MO orbitals, and these electron gaps are really, really tiny. But eventually, when we have so many of these atoms that are interacting like a solid, okay, we can have this continuum, and sometimes you have the overlap. All right, now, once you have the continuum of all of these orbitals together, that will decide what kind of gap you have based on the continuum of one to the other. Now here's 3s to the 3p, but it could be to the antibonding as well. Like we talked about earlier, oxygen's 2 electrons were in its antibonding, it was able to jump. There was a little gap here, but that's not really gap theory because that was just basically 2 atoms, okay, interacting. All right, so it is the width of these bands and their proximity to existing electrons that determines how mobile these electrons when exposed to electrical field. So the idea is that these are mobile electrons that can occur in these bands. And it only occurs under a set of conditions. And those conditions are that they're kind of interconnected, so to speak. They can't be single atoms close to each other like this is saying. They have to be interconnected. So I'm not loving this. All right, moving forward. Maybe. So here's our valence conductive band, and there's a significant leap of energy into this energy gap or forbidden area. This represents something, if it's a big enough, like a nonmetals. And of course, a large effective nuclear charge would do that. And of course, if there's a big enough gap and it's hard for electrons to move from this continuum to this continuum or this band to this band, a big enough gap, this would be an example of electrical insulators. So these are hard to get from one to the other and jump back. So as a result, we would see electrons are more strongly bound. And of course, this occurs with high effective nuclear charge atoms of the nonmetals. So here's a great little diagram here where we have metals where the gaps are overlapping. So it doesn't take it takes very little energy to get to the overlapping, if any. Semiconductors have a gap, which means they have a tough time getting there, but they have the ability. And then, of course, real nonmetals, smaller atoms with high effective nuclear charge, their gaps are just too big. Their band gaps are too big. They're not good conductors. So metals have a very small gap or just an overlapping gap. A semiconductor, as it says, it's not a great conductor, but it's somewhere in between that of the overlapping of metals and the big, huge gap. So they can have some conductivity, and we're going to learn that if we dope a semiconductor, help it, okay, we can actually change its conductivity by doping it, all right, and we'll get to that in transistors. That's where we're headed. So MO theory and stacking the MO orbitals creates the bands depending upon the properties of the effective nuclear charge or how these atoms can interconnect so they can stack their orbitals together depends upon the size of the gap, but the size of the gap drives the conductors from the semiconductors to the terrible conductors called insulators. So hard for these electrons to get to this level, so therefore they tend to insulate heat and electricity. Okay, so going on to 2 common allotropes of carbon are graphite and diamond. Okay, now diamond's hard to look at, but if you look at carbon is bonded to other carbons in a crystal, and if you notice, it's bonded to 4. So this is sp3. If you look carefully, 1, 2, 3, 4, this is a tetrahedral that keeps going in all directions. So this tetrahedral going in all directions creates, okay, this gap, or I'm sorry, creates basically an interconnection of carbons with each other. So all the carbons bonding orbitals will band together to make a continuum. Just as graphite looks a little different, graphite, if you look very carefully, has a central carbon bonded to other carbons. Okay, so these compounds are rare in the sense that This is carbon bonded to carbon, what we call sp2, right? Because we have a carbon here bonded to 3 other carbons. You can count there. There's your trigonal planar. Here we have a carbon bonded to what? 4 other carbons. So this is sp3. Okay? But the bottom line is we're going to create bands or continuums because these carbons are totally interconnected. Every single one of these carbons, okay, is sharing what? Or is adding to the MO diagrams. So therefore, we're creating bands. The question is, what kind of gaps are we going to have? As we talked about, diamond has a significant gap, so therefore, electrons have a tough time moving to this vacant band, where graphite doesn't, and I want to understand that. Graphite, now sp3, these are all covalent bonds. By the way, these are called network solids, okay? Because it's a network of covalent bonds. Kind of weird because most things that are crystals, solids, are usually metals or ions, not things that are non-metal. But back to reality here. This is sp, I should say 2. Not sure what happened there. It's sp2. How do these sheets of carbon work? By the way, we have graphite in our pencils, and they rub off layer by layer. Now, if it's sp2, what do we know, party people? That there is an unhybridized what? There's an unhybridized p that's above and below. So every one of these carbons has an unhybridized p. So these have unhybridized p. So really what you have, party people, I'm not sure why I'm zooming in, but I am. Okay, what you have is you have these p orbitals interacting with the other carbon's p orbitals. Now, not going to say it's pi bonding, but what we'll say is that there is an attractive forces existing. We think they're dipole-dipole interactions, but basically electrons are able to move throughout these p orbitals. Okay, if everyone gives off a p orbital pointing downward, right? These electrons can move throughout these p orbitals and be what we call delocalized. All right, and to see what I mean, let's go on to the next slide, maybe. So here's my carbon, here's my graphite, here's my sp what? 2, and how does it interconnect with the next sheet? You can see the sp2 trigonal planar right there. It's got these unhybridized p's that interconnect and make those electrons really delocalized. Okay, so if we go on to the next one, so there it is. Take this trigonal planar carbons, and here's the planar carbons. Notice the hybridized p's. So these electrons are free to what? Migrate, which means these electrons are totally interconnected, and what we have is we have something called pi stacking. We're going to stack all these pi bonds in our MO orbitals. So diamond doesn't conduct electricity because the gaps are too big. The sp3 hybridization does not allow for any delocalization. So therefore it limits the banding, so there are no large gaps. Okay, but what do we know? But in graphite, sp2, with this unhybridized p, where electrons are free to move around like resonance, and look at this, double, single, double, single, double, single. That's called a conjugation. When you have double, single, double, single, double, single, that means there's always a scenario where each carbon has an unhybridized p. I'll say that again. When you get a double, single, double, single, double, single, and this interconnects, all of these carbons must be sp2 hybridized, and they all have an unhybridized p. So unlike sp3 diamond, sp2 graphite has a way for electrons in these pi bonds. Remember, every double bond is a pi bond. So really, these pi bonds are resonating. There's a resonance structure. Look at this, party people. It's going from this to this, back and forth. So really, these electrons are able to move throughout the what? Unhybridized p orbitals, which means all the pi bonding orbitals are going to stack up nicely and make tremendous bands of very wide width because there's so many of them. The electrons are free to roam, and because of that, the gaps that we're going to make are going to be small enough for electrons to jump from a vacant band. And so, my friends, in chemistry, okay, we're going to be able to create tremendous bands because of what we call pi stacking. Pi stacking is that so many of these electrons are free to roam, okay, and have delocalization. And we call this I can write here, maybe. And we call this conjugation, okay? Anytime we have unhybridized P's, and again, we always have with a double single conjugation, that sp2 carbon results and allows for electrons to be delocalized. It allows for all of these pi bonds to be part of the same MO diagram, and therefore you're going to stack all of these orbitals into a major continuum, and there's so many of them that there's a great chance that band is going to be so small, and therefore graphite conducts electricity, okay, whereas diamond doesn't. All right, very important. So if you're in an electrical storm, take your pencils away. That's right. All right, so moving forward here, party people, okay, this conjugation opens up something called chromophores, maybe. So let's get out of this. And diamond doesn't conduct for reasons we just talked about. And now let's look at something called chromophores. So these are conjugated because of their continuous double and single bonds. But what does that really mean? Double and single bonds means we have some type of sp2 hybridization. Now what you're looking at here, party people, is you're looking at organic molecules. These corners are carbons. So you can see that this is a carbon and it's bonded to 1, 2, 3 places. These are sp2. So every one of these carbons, right here, right here, right here, right here, because of conjugated double and single, you have unhybridized P's that allow electrons to be delocalized, which means you have a lot of what? Pi stacking, or a lot of the same pi bonding being the same molecular orbital, and that makes the gap smaller. So if we look at something like benzene, okay, if you look at the double, single, double, single, double, single, benzene is hybridized. Benzene has resonance, and it has these sp2. Now, so Mr. Grotsky, I don't see the 3. There's going to be an electron that comes off this. And these type of diagrams, they don't show the hydrogen. So with a hydrogen coming off this corner, and this corner is a carbon, these corners are all sp2, which means they all have unhybridized P's that allow electrons to go in a circle. Okay, and that's why sometimes they'll write benzene this way. Okay, they'll write this, and sometimes, remember, I can put a double bond here, double bond here. Remember, the corners are the carbons, right? Okay, this is not a pretty drawing, but neither am I. And of course, you can put the hydrogens on each carbon. Okay, so that's where you get your trigonal planar from, or your sp2. Here's one bond for this. This carbon goes to this carbon, this, and there's a double bond here. So there's your trigonal planar. But more importantly, this would make a what? Resonance structure, right? Because you can go double here, and double here, and that's how they would draw it. They wouldn't put the H's in front, they don't put the C's. Now some people would write benzene like this, and they put a ring in the middle to show that those electrons from double to single to double, conjugated, okay, allow electrons to just kind of continuously move. So benzene has some conjugation. Therefore, it's going to have some continuum of those pi's. But those gaps are going to be pretty big. And so benzene, if you look up here, absorbs spectra in the 200 to 300, well, I don't know, about 250 range. Okay, so that's not really in the visible spectrum. That is a pretty, this is wavelength, so the wavelength is too small, so it's really, really, really beyond the visible spectrum. So you would say that this is probably in the ultraviolet spectrum, it absorbs energy, so that's why benzene is going to be clear. Now anthracene, you notice, it has more conjugation. Again, look at these corners. These are all sp2 carbons, so they have the ability for electrons to travel through all of their unhybridized p. There's more conjugation, so there's more pi stacking. There's more orbitals, just like we did lithium, lithium-2, lithium-3, and you saw the gaps become small and small until it was a continuum. So these are making more of a continuum, and the gaps are kind of what? Smaller. So now the wavelength it can absorb is bigger. Bigger wavelength, lower energy, smaller gaps. Look at chlorophyll. A, talked about this in AP Bio. This has a lot more conjugation than anthracene. Now, not all over, but look at from here to here to here to here to here. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I can keep going. Look how many places the pi bonds, okay, can interconnect. So there's a lot more pi stacking here. So therefore, chlorophyll A, okay, can absorb, okay, in a even smaller energy level, okay, in the red part of the spectrum, okay, and also, I'm sorry, this is the blue part of the spectrum, and this is the red part of the spectrum. Doesn't do well in the middle, but, and that's because of its complicated shape, because it has some conjugation that's kind of tied off and some that can go around in the circle. But the bottom line is, it's more in the visible spectrum. It's more with the wavelengths that have what? Longer wavelengths, lower energy. Therefore, the gaps are what? Smaller. So benzene can absorb only big energy photons like ultraviolet because the gaps are too big, because there isn't a lot of connected orbitals. But as a number of connective orbitals and unhybridized p's and more delocalization, because of this conjugation, the gaps get increasingly smaller. Okay, very important. So pigments or chemicals in our that we use that have color are able to absorb parts of the color because their gaps are smaller. Okay, so if we look at organic pigments or dyes, this is an oil dye, which means it's blue because it absorbs the yellow part of the spectrum. Can we see something? Can we see conjugation? Yes, you bet you can. These are all sp2 carbons, so the electrons are free to roam, okay, which means it absorbs the yellow part of the spectrum. It's got a very small gap. Now, if you look at other dyes, okay, here's green. Wow, that was yellow. Now, this has even more conjugation, so the gaps are even smaller. But again, there's a little more complexity here with the N. So what you're seeing with these organic dyes is the idea that electrons are free to move through these pi bonds because of what? Because of conjugation or resonance. This delocalization of electrons allows all those MO orbitals to make a continuum. And the more you have, the smaller the gap, and the ability to do what? Have a small gap from your vacant to, or sorry, from your valence band to your conductive band or vacant band. So all of these organic pigments that we know of all have something in common. They have conjugation. We call these chromophores. We call these all dyes. And so we talked about early in the course, very interesting, about the transitional elements making colors. Well, these are how colors are made with organic or nonmetals. They have to have pi stacking in MO diagrams to create band gaps that are small enough. You have to have interconnected electrons sharing essentially the same energy level. So all of these dyes are connected by that. So this is beta carotene, sp2 all the way. Obviously, if you take too much vitamin A and beta carotene, you glow in orange. So you can, and because it's a fat soluble vitamin, because most of this is nonpolar. But the bottom line is the red carrots or summer squash are red because of conjugation. The double, single, which really means what? sp2, sp2, sp2. Trigonal sp2. That means all of these electrons are in the same energy level. And you stack of them all, okay? Make small gaps, okay? Our acid-base indicators change colors based on changing the gaps. Notice phenolphthalein is colorless. Yes, there's like a benzene ring here, here, and here, but they're not connected, okay, in this pH here, okay? When a pH is acidic, it changes the structure, so these gaps or these electrons here are not connected. And think what happens. In a basic pH, the structure changes so that now, oh my gosh, we're interconnected throughout. That is so cool. So phenolphthalein turns color because it changes its structure in different pHs to allow for more what? Conjugation. There's gaps here, but these gaps are too big because they're not interconnected. By being at a pH of 8, now you're connecting the entire molecule's electrons, and there's more what? Pi stacking here in the bonding orbitals to make a bigger continuum and smaller gap to get wavelengths of light. I find that to be fascinating. Okay, so all of our acid-base indicators change their way of conjugation or pi stacking in their MO diagrams to be able to take more or less of the wavelengths of light depending upon the gaps. The gap is changing based upon acid and base or pH of the solution they're in. And of course, someone asked me this question a long, long time ago. Why does bleach, sodium hypochlorite, make our clothes lose their color? Well, sodium hypochlorite breaks apart into Na plus and the hypochlorite ion. This is -2. This is +1 ion. This is a what? Electron sink. And what electrons are they going to pull from? Christmas in July. They're going to pull from the pi bonds first because they're outside of the what? Nuclear envelope. And if you pull electrons in the middle of this beta carotene or any kind of dye, and you break up the conjugation so they're not interconnected, you're going to make that continuum smaller. Keep doing that. All right? Just like we go back to phenolphthalein. There's a continuum, a band, but it's too small. Until you interconnect them so that all of these are sharing the same space, that's when the continuum gets big enough and the gaps get small enough. So if you drop this oxidizing agent, which pulls electrons, makes this lose electrons from the pi bonds, and now make this single bonds, these electrons here cannot connect here, and now the continuum gets smaller and the gap gets bigger. Hope you can understand that. So you should know why, walking out of this, why bleach takes our colors out. By the way, okay, cosmic rays and sunlight makes our clothes that have these pigments become what? Become lighter over time because we lose the electrons from the what? We lose the electrons from our pi bonds first. So even oxygen over time, okay, will take these electrons out of our chromophores and cut these bands into bigger bands because electrons are not interconnected, okay? So it's pretty cool, all right? And chlorophyll, of course, important pigment, has these bands. And of course, the color of our blood, hemoglobin, okay, basis is a ligand, okay, but the bottom line is you have this interconnectivity of these carbons, sp2 carbons all the way through. And that creates the ability to absorb wavelengths of light, all right? So hopefully you learned something here today that of course, transitional metals, because of crystal field theory, create little gaps within the same d orbitals, but all of our organic counterparts, our carbon-based molecules, if they're sp2 and are conjugated like this, all the what? Pi electrons are interconnected into the same MO diagram called pi stacking that creates a band gap. And if there's a lot of them, that gap's going to be, well, the band's going to be big, which means there's a great chance of what? Having a smaller gap in between to absorb wavelengths of light. All right, so I am done here, okay? I hope you understand at least some of that.